So let's first start with problem 822 and discuss the general idea of torque. A torque is a vector and it is defined as R cross F. And I have to be a little bit more specific. A torque is always relative to a point, and let's assume there is a force here. Then the definition of the torque relative to this point, this is the position vector, so to speak, measured from P. Then the torque relative to point P is the cross product between R, this vector, and F. And if this angle equals theta, then the magnitude of the torque, not talking about the direction, equals the magnitude of R times the magnitude of F times the sine of theta. As far as the direction is concerned, it's always perpendicular to both F and to R, so it's perpendicular to the plane of the paper. And in this case, if you remember how to apply the rule of cross product, the torque vector is in the paper, which we would indicate with a circle and a cross. You're looking at the tail of an arrow that went into the paper. If it were out of the paper, then I would indicate it with a circle with a dot. You see the tip of the arrow. The torque can be positive, can be negative. You can see that immediately depending upon the sign of sine theta. If I had a point Q here, then the torque relative to point Q would be negative. And so the torque would be coming out of the paper. In our case, the torque P is larger than 0. And you can have torques relative to points which are 0. For instance, if I draw a line here, extension of what I call the working line. In high school I was taught that the line along which the force acts is called the working line. Any point A that you have, doesn't matter whether you have it here, or here, or here, it's immediately obvious that the torque is 0. Because r sine theta, that is this distance, I call it often r perpendicular. And you should be immediately convince yourself that this is r sine theta. And so for all these points A on this line, r sine theta equals 0. And so the torque is 0. If I chose a line perpendicular to F, perpendicular to this working line, and I had here a point P1 and a point P2 and a point P3, then the torque relative to point P would be the torque relative to point P1, would be the torque relative to point P2, and so on. For the simple reason that they have, first of all, the torque is always positive, and the simple reason is that R perpendicular is the same for all these points. So I hope that this will help you a little bit in getting going on this problem. Now I want to address some special cases. Let us suppose that we have that F2 equals F3 and that they're parallel. So here I have a point P and here I have a force F2 and here I have a point, a force F3. It doesn't have to be exactly going through this point. By the way, this distance is the same as this distance. I could have a force here, F3, same in magnitude. And just to make it even a little bit more complicated, why don't I also have a force whereby the work line goes straight through point P? It should be obvious now to you that the net torque relative to point P equals 0. If I think of the torque P due to force 2, which gives me a rotation, it is a clockwise rotation, the torque would be larger than 0. then you can immediately see that tau 3, if F3 and F2 have the same magnitude, is a counterclockwise rotation. It is negative, the torque, and the two cancel each other. And F1 goes straight through F, so R perpendicular is 0, so clearly there is no contribution to the torque due to F1. I want you to notice, though, that the sum of all forces is not 0. So here you have a situation that the sum of all torques is 0, but that the sum of all forces is not 0. And if these forces acted on an object of which P was the center of mass, it was some kind of an object, and P was the center of mass, then there would be no rotation, but this point P would undergo a pure translation, the whole object would undergo a pure translation with constant acceleration along a straight line. And so now the question comes, is it possible that the sum of all forces is 0, but that the sum of all torques is not 0? Of course, that is also possible. And I will show you an example of that. So the sum of all forces is 0, but now the sum of all torques is not 0. Suppose we have here point P. This distance is the same as this distance, and I have a force F1, which is in this direction, and I have a force F2, which is in magnitude the same, and it acts along a line which is parallel to the working line of F1, and say the force is here, F2. Now the torque 1, P with this point is positive, it's clockwise. The torque 2 is also clockwise, so there is clearly going to be a rotation, there's no way around it, yet the sum of all forces is 0. And so you see, according to Newton's law, which says that the sum of all forces total equals m times a total, well, this is 0, so there is no acceleration. So it's only going to rotate, but it's not going to translate. In this specific case, no matter where you choose a point A, or Q, or B, this is a very special case, you can easily prove that the tau relative to point P, the torque, is exactly the same as the torque relative to point Q, is exactly the same as the torque relative to point A, no matter where you put them. And the magnitude of that torque, of course the torque is in the paper, it's a clockwise rotation. If I call this separation between the two L, then the magnitude of that torque, no matter which one you take, would be F1 times L, but F1 of course also in magnitude is the same as F2. But that's a very special case. Torques are key in rotation, and we will see several examples of that today.